Hello students, my name is Shashank Shekhar. So we have started the long form of periodic table or the modern form of periodic table. Now we'll get more into the structure. Okay, so we know that there are 8 vertical columns and 7 horizontal rows. Okay, and they have been obtained by arranging the elements in order of increasing atomic number. And the vertical columns are known as groups, and the vertical and the horizontal are called as periods. Right? So we know it. So each group consists of a number of elements having the same electronic configuration. So if I take one group, suppose I'm saying it at, suppose we are going through the old way of classification, that 1A, 2A, 3A, 4A up till 7A, then 1B, 2B up till 7B. So if you go through that, then one in the same group, suppose I'm taking 1A, okay, then each of these elements will have the same valence electronic configuration. Again, I'm saying it, there will be some disparity, but ignoring those disparity, we are very good with this approximation. Okay. Now, these groups are numbered again from 1 to 18 also, or we can name this 1A, 2A, 3A, 4A up till 7A and 1B to 7B. Now, the elements of the first two groups, one for group 1 and group 2, which are on the extreme left, which involves the filling of s orbital, while those on the last group from 13 to 18, they involve the filling of the p orbital. The element of these 8 groups, that is 1, 2, 13, 14, 15, 16, 17, 18, are collectively called normal or representative groups. Okay, so we are not talking about the middle one, which are flanked by these two columns, but we are talking about the left 2 columns and right 5 columns, 6 columns. Okay, so 1, 2, and then from 13 to 18. So they are called as collectively called as normal or representative group, and their outer electronic configuration is, so if we talk about 1, so it will be NS1. If we talk about 2, it will be NS2, 13, NS2, NP1, 14, NS2, NP2, 15, NS2, NP3, 16, NS2, NP4, 16, NS2, NP5, and 17. Okay, so I think we are missing something here. So 13 means NS2, NP1, 14 means NS2, NP2, then this is NS2, NP3, NS2, NP4, NS2, NP5, and this is NS2, NP6. Okay, so this is what are we seeing here? That the last digit, suppose I am taking it as 13. So we'll take the last digit of 13, which is 3, and that will be the number of electrons that are present in the p orbital. Okay? No. Okay, so this is not the one. So what I'm saying is that, uh, so if you just look here, then if you look at the last digit of the number, so if you take 1, so 1 is the last digit, then these are the number of electrons that are present in the valence shell. About 2, 1 is the last, 2 is the only digit, so 2 will be the present that number of electrons that is present in the valence shell. If you take 13, then 3 is the last digit. Okay, then 3 electrons will be present in the valence shell. So if you see here, NS2, NP1, so total this two subshells will constitute total of 3 electrons. What about 14? The 14 has last digit as 4, so the number of electrons in the valence shell will be 4. So NS will contain 2 and NP will contain 2, total of 4. Same for 5, so 2 plus 3, 5. Same for 16, 2 plus 4, 6, 6. Same for 17, 2 plus 5, 7. And same for 18, that is 2 plus 6, 8, right? Okay. The elements of the group 18 are also called inert gases or noble gases, as their valence shell is completely filled. That is NS2 and NP6. What about the elements of group 3 to 12? So they are called transition elements, since the properties lie in between the properties of reactive elements, okay, that are present on the extreme left, and the non-metals which are present on the extreme right, like the chalcogen family and the halogen family. So these elements are between in this transition from going to the most reactive to the non-metal. They fall in between, so they are called as transition metal. In these elements, both the outermost shell and the penultimate shell are incompletely filled, but filling the d orbital of the penultimate shell occurs. Okay, so this is the way that the filling occurs. So the ultimate shell, so this is the ultimate shell, n. Okay, nth shell is the ultimate shell, and the penultimate shell is n minus 1. So filling of both these shells occur in this 3 to 12 group. Okay. Now two series containing 14 elements are placed at the bottom. We have seen it. So in this case, what happens? Their general electronic configuration is the outermost shell. Okay, the outermost shell in both this series, the outermost shell and the penultimate shell. So these two are the penultimate shells, and the outermost shell is this. They both are filled. Okay, they both are filled in the progressive way. The first series goes from 58 to 71, which occurs in the periodic table after lanthanum and are called as lanthanoids. Whereas from 90 to 103, they occur after actinum and they are called as actinoids. And since they are in between the transition and the reactive metals and all, so they are called as inner transition metal. Next, so this was all about groups. Okay, so we talked about groups. Now what about periods? So if we talk about periods, as stated above, the long form of periodic table consists of 7 horizontal periods. So we have seen it, which is 1, 2, 3 to 6, sorry, to 7. Each period will consist of series of elements whose atoms have the same principal Compton number. So this is the similarity between the group elements which are present in the same period, is that their number, means the principal Compton number, is same. Okay, so if you are filling say 3D, then if you are filling third shell, then we will fill the third shell only. So subshell can vary, of course subshell can vary, but the shell will not vary, right? For example, the first period correspond to the filling of the first shell. So n is equals to 1. The first shell is filled in this case, right? So it consists of only two elements, hydrogen and helium. So if you talk about the second one, so it will have n is equals to 2 value, and in this four four orbitals are present. So one of 2s and 3 of 2p. So which can accommodate total of 8 electrons. So therefore 8, there are second period contain 8 elements. So whatever will be the number of orbital in that shell will be the whatever will be the number of electrons that can be filled in that shell will be the number of elements that will be present in that period. What about 3? So if we talk about the second period, so it will have lithium, which will have a atomic number of 3, which has one electron that enters the 2s orbital and ends up with neon, which has completely filled 2s and 2p orbital. So 2s and 2p subshell. The third period correspond to filling of the third shell. So third shell will have how many electrons? Say the formula is simple, 2n square. So 2 into 6, 3 square, that is 9. So 18 elements should be there, and there are 18 elements in those. So this shell has 9 orbitals, 3s, 3p and 3d. So 1 3s, 3p orbital and 5 3d orbital. However, we know from energy level diagram of multi-electron system that 3d orbital have even higher energy than the 4s orbital. So this way we have studied in the structure of atom. Okay, so we have seen that how n plus l value decides it. So we will not go to that again. But we know that. Okay, we know that. Therefore, the 3d orbitals are filled before 4s orbital. So that is a different thing. So consequently, in the third period involve the filling of 4 orbitals, 3s and 3p, and thus contain 8 elements from sodium to argon. Now the fourth period consists of filling of fourth level, right? Okay. So here we have how many elements? 18 elements, right? Up till 18. Sorry, not 18 elements. So we're starting from 11 and moving to 8. So total there are 8, right? Total there are 8 because 10 are already been placed. So we'll not call it 18 because 10 are already been placed in the upper one. The fourth period means n is equals to 4. So 4n square will give a value of how much? So 4 for the 16, 16 for the 64 elements, out of which 18 are been already placed. So 18 to the how much? So 18, I think 18, 864 minus 18 will give the element that will be present in this period. Clear? So first of all, 4s will be filled, right? Then the filling of the 5 3d orbitals begins, right? Because it has a lower energy, then of p orbitals higher than that of 4s. Further, the filling of 4d and 4f occurs, right? Therefore, in the fourth period, the filling of only 9 orbitals occur, which can accommodate total of 18 electrons. Clear? Next, therefore, the fourth period contains 18 elements from potassium to krypton, 19 to 36. The fifth period, like the fourth group, also contain 18 elements. It begins with rubidium and ends up with xenon. So what about the extra electrons that can be added? So they go to the inner transition element. Okay, so we will see it that they go to the inner transition element. The sixth period also consists of sixth level. So again, there are extra electrons. Okay, so they will again go to the uh, inner transition elements. Clear? So what do we do here? So we start filling the 6s orbital. Okay, we start after filling the 6s orbital, the electron enters the 5d orbital. Okay, and thereafter the filling of 4f orbital begins with cerium and ends up with lutetium. Right. So in this, so when we start filling the f orbital, so in this process, we end up filling 18 electrons, and that sorry, we end up filling 14 electrons, and that results in 14 elements that constitute the first series of say lanthanoid. Okay, that are called 4f inner transition series. Now they are separated from the whole frame. So if you look at the periodic table, you must have seen that two of the rows are placed on the bottom. Okay, so those two rows, the first row in which the 4f orbital is filled is called as the lanthanoids. Okay, or the lanthanides. Now talking about the seventh group, seventh period. So like seventh period, it is also accepted expected to contain 32 elements corresponding to filling of 16 orbitals. So from 17s, 75f, and 560 and 37p. However, this period is still incomplete. Only 28 elements are known in this 7th period. Now, how it is filled? So first of all, 7s filled. Then after that, we fill the 6d, and then in the further process, we fill the f orbital. Clear? Now this again we have f orbital. So these are 5f orbital. Initially we have 4f orbital, and these are 5f orbital. Now this series in which the 5f orbital is filled called as actinoids. So they start with proactinium and ends with lawrencium. So although thorium Z is equals to 90 does not have any electron in the 5f orbital, yet it is considered to be a F-lock element. So thorium have no electron in the 5f orbital, but still they are what? They are still 5 F-lock elements. Now, since its properties, because why is it so? Because its properties represent more the f orbital rather than d block element. These 14 elements from thorium to lawrencium constitute the second inner transition series. The first inner transition series is for lanthanoids, and the second inner transition series is for actinides or actinoids. Now, it mainly includes man-made radioactive elements. Since these are man-made, means that are added artificially synthesized and not naturally found. Now, in order to avoid the undue expansion of periodic table, actinides like lanthanides have also been separated at the bottom. Okay, so means to make it look more decent, so we have placed it in the down. Okay, we have placed it in the separate panel in the down bottom panel. Okay. Also, since they have a different properties, since it includes the filling of f orbital, they have difference in the properties, of course. So we cannot place it anywhere in between, and for that reason, we have placed it in a separate panel, which is in the down section of the periodic table. Clear? The first three period contain 288 elements respectively are known as short periods, while the next three periods, which contain 18, 18, 32 elements respectively, are called long periods. So for first period, we have two elements, which is hydrogen and helium. Now, hydrogen is still having no place because of the difference in the chemical and physical properties, but still they are considered in the first period only. And for that reason, they are placed in the, so its group is unknown, but still its group is unknown. We cannot place hydrogen in the first group. It is away from that group, but period is fixed. It is in the first period. Okay. So the first period contains two elements, second period contain 8 elements, and the third period also contain 8 elements. Whereas the next three period are 4th, 5th, and 6th. 4th contain 18, 5th contains 18, and 6th contain 32 elements, and they are called as long periods, whereas the 2, 8, 8 are called as short periods. Next is electronic configuration of elements and the periodic table. Okay, now we will talk about the electronic configuration. Now, an electron in an atom is characterized by 4 quantum number. We know it, which are principal quantum number, azimuthal quantum number, spin quantum number, and magnetic quantum number. But the shell in which the electron goes is decided by the principal quantum number, which is n. N can be 1, 2, 3, 4, up till infinity. Next, we have different subshells, okay, like S, P, D, F, in which we have orbitals. So S subshell has 1 orbital, P subshell has 3 orbitals, D subshell has 5 orbitals, and F subshell has 7 orbitals. Now the distribution of electron into orbital of an atom is called as electronic configuration. So each orbital can contain 2 electrons, and the distribution of those electrons in this orbitals are called as electronic configuration. An element's location in the periodic table reflects the quantum number of last orbital filled. We will observe a direct connection between the electronic configuration of the element and the long form of periodic table. Okay, so of course there are some disparity, but still they are filled progressively. Means they are filled progressively, but it might be possible that initially the electron was going to the 4f, but it may not go to 5f, but it may not go to 5f in the next series. So this is possible. Okay, this is possible, and there are anomalies. So as we go down for heavier element, these anomalies have much more significance. Now, if I talk about the electronic configuration period, the period indicates the value of n. So if I talk about the first period, then it is the first subshell that is first shell that is filled. If I talk about the second period, then second shell is filled. Similarly, 3, similarly 4. Now it can be readily seen that the number of element in each period is twice the number of atomic orbital. Okay, so if the number of orbital is say s, okay, so if it in s or s subshell we have 1 orbital, the number of electrons is 2. In p subshell we have 3 orbitals, so number of electrons is 6. So the number gets twice. Okay, we know that. Now the first period n is equals to 1 start with the filling of lowest level, which is 1s. That's the lowest level and has 2 elements, hydrogen and helium, 1s1, 1s2. That completes the K shell. The second period n is equals to 2 starts with lithium. First of all, the electron enters the 2s orbital. Okay, the next element is beryllium, has 4 electrons and has the electronic configuration of 1s2, 2s2. Starting from the next electron, the 2p orbital are filled with electrons when the L shell is complete. Now, if I talk about the boron, the 2p orbital are filled with the electrons when the L shell is completely filled. It is at neon, which is 2s2, 2p6. Thus, there are 8 elements in this period. Okay, starting from 2s1 ending to 2s2, 2p6. The third period begins at sodium, and the added electron enters the 3s orbital. Okay, the successive filling of 3s and 3p orbital give rise to third period of the 8 element from sodium to argon. So we go from 3s1 to 3s2, 3p6. So starting from potassium, the electrons, if you go to the fourth period, then we have what? We have started at potassium, in which we are filling the 4s orbital. Now the 4p orbital is filled before filling up of the 3d orbital. Right? Note that before the 4p orbital, the 3d is filled. So this is energetically favorable. So first 3d is filled, then 4p is filled. And we come across the so-called 3d transition series of elements. So they start from scandium, which has electronic configuration of 3d1, 4s2. Okay. In the fourth period, end up to krypton, in which the 4p orbital is completely filled. Although we have 18 elements in this fourth period, okay, the fifth period begins with rubidium. okay, rubidium is similar to the fourth period and containing 4D transition elements. Initially we have 3D, we have now 4D. And this 4D transition element starts from yttrium. The 3D orbital are filled with zinc with an electronic configuration of 3D10 4s2. Okay, so there we have completely filled 3D orbital at zinc. This period ends at xenon, filling up with the filling of 5p orbital. Okay, the sixth period contains 32 elements. We know that, and the successive electron enters the 6s, then 4f, 5d, and 6p in the order filling up. We are going from n. We are going through n plus n rule simply, and if n plus l value is same, then one with the smaller value of n has the lower energy. Then we have the filling of 4f or orbital, which begins with cerium and ends at lutetium. We have seen that to give the 4f transition series. The seventh period is similar to the sixth period. So there is successive filling of 7s, 5f, 60, 7p. Okay. Now this period will end at the element with an atomic number of 118, which would belong to the noble gas configuration. Now in the filling up of 5f orbital, we have seen that they have given rise to inner transition element. The same thing is written. So now we have initially we have seen this same thing through the medium of say our groups and periods. Now we are seeing it through the medium of electronic configuration. Okay. Now the 4f and 5f inner transition elements are placed separately in periodic table. So we have seen it already. I will not repeat it. Question: how would you justify the presence of 18 elements in the fifth period of the periodic table? So of course, this is very obvious. So since n is equals to 5, L is 0, 1, 2, 3, 4. These are the possible values of L. The order in which these orbitals are filled is 5s, 4d, 5p. The total number of orbitals are 9. So therefore, 18 electrons can be filled. That results in 18 elements. Group-wise electronic configuration. So what is group-wise electronic configuration? The elements in the same vertical group or column have similar electronic configuration. The same number of electrons in the outer orbital, and therefore they have the similar properties. For example, group 1 elements all have ns1 configuration. Okay, it is shown here. See, they have all ns1 configuration. N stands for the period which we are talking about. This can be seen that the properties of the atomic number are in accordance with the properties of the elements are in accordance with the atomic number. Okay. So this was for today's class. With this, I end my lecture. Thank you.